Willkommen alle zur 1, 2, 3, 4., 5., 6. Woche Einführung Krypto. Was wir letzte Woche gemacht hatten, wir hatten angefangen, den DES-Algorithmus durchzunehmen. Da hatte ich ja auch länglich drüber geredet am Anfang. That this is a very important algorithm. I am flexible. So, and what we essentially did is we looked at DES on 3 different levels. So we started with an extremely high-level view, saying this is a block cipher, 64-bit in, 64-bit out, and a key. And then we zoomed a little bit more in. We got a little closer, and we saw this structure. Does anyone recall what the name is of the structure here? Feistel, exactly. That was Horst Feistel, a German emigre in the US. And then we zoomed inside the F function here. So if we thought that this is at the very heart of DES is the F function, okay? So, and then what you could do in your homework assignment, you could actually almost do an encryption and decryption. There are only a few things missing that we didn't finish up, and that's what we're going to do today. So today, again, this is entirely devoted to the exciting data encryption standard. Can we calm down from now on? Also up there. Thank you. So there are 4 topics that we have. So the one big thing that we haven't done is we want to talk about the key schedule. We want to talk about, once we have encrypted, we have to decrypt on the receiver side. There's decryption. There's decrypt. And then kind of smaller topics are the DES security. So I want to discuss attacks. And kind of a very practical, final, very small chapter will be DES alternatives. So what can we use? Alternatives. Okay. So there are kind of 2 real technical parts of this lecture today, the key schedule and DES decrypt. So you have to be very alert and awake for that. So you have to learn something. And topics 3 and 4 are more or less factual knowledge, what I want to convey. Okay. So let's start. With the first section, namely the DES key schedule. Okay. If you look again at the main picture of DES that we used last week, okay, so this is the Feistel network up there. Does this look less stupid? Yeah, it looks less stupid. Okay, so what is the key schedule? The key schedule is essentially what you see on the right-hand side here. Okay, so you go in with an original key, K, and what we have to do, we have to compute or to derive ableiten, right? We have to compute 16 subkeys, K1, K2, up to K16. So that's what we're talking about. Question is how to compute the 16 subkeys K1 up to K16 question mark. Okay, and I think we can. I start with just showing you how that works. This is great. Okay, it's not on here. You see where that's on the PowerPoint slide. Okay, here we go. 1 second. Okay. Okay, so what you see on the right-hand side here, this is a key schedule. Okay, so and I can. Oh yeah, most of you got the book, right? Book is available. So this is figure number 314. So what you should see, what should be in your lecture notes here is figure 3.14 in the textbook. Okay, so this is what you see on the slide in a somewhat nicer version. That's the key schedule. You see, we start with the original key, and then we see somehow K1, K2 up to K16 is being computed. And now I want to discuss this block diagram with you. Okay. One thing that's noteworthy is the key schedule consists of simple operations. Okay. So we start with, if you start at the top at K, what might confuse you, if you're very, very alert, there should be a somewhat of a conflict. At the very top of this picture, can you read the bit length of K? What does it say? What's the number there? 64. But what I've been telling you, since last week, where is it here? This is 56 bits here, right? This says 64. So what's going on? And that's a very confusing fact, and it's not very nice if you teach cryptography that the DES standard has as an input 64 bits. So what's happening here? We go in with 64, and you see this block PC1, PC-1, PC-1, and what comes out is 56 bits, right? So and what's happening here is, let's start with number A here. We talk about this PC-1. This is permuted choice 1, which is, again, this block that you see over there. What happens here is this drops bits number 8, 16, 24, up to 64. Okay? Drops heißt fallen lassen. Okay? So they're not connected through. So you go in with 64-bit, but every 8th bit, bit 8, 16, 24, 32, and so forth, are not connected through. Okay? So you can put whatever the input is, those bits are being ignored. Okay? Drops bit, so. Okay? Effective key length of DES is, of course, 64 minus the 8 input bits that are not connected through, and it's a very weird thing that's happening, is 56 bits. Okay? So the big question is why? I don't really know why. Okay? It's in the literature, particularly the older literature, they talk about these bits serving as parity bits. You know parity bits? I think they did that in Grundlagen in Informationstechnik, right? Professor Martin. And it doesn't make much sense that there is a parity check part of an encryption standard. I don't know. Some people who love conspiracy theories, who believe it really nasty NSA, some people think that was put in so that people think it's a 64-bit cipher, which is more secure than a 56-bit cipher. But I don't know, okay? So what's important for you is never ever think that there's a 64 bits. It's not a 64-bit cipher, 56, okay? And it's, or the rest, what happens with the other 56 bits that are connected through, they're also permuted, they're cross-wired in some funny way, okay? So, and again, no, it's not on the slide here, but of course it's in the book, you see how PC1 works, okay? So this is essentially historische Artifact, right? Some kind of weird thing that happened historically and cryptographically that's not important. Now it's getting interesting. What you see is that the 56 bits are split in two halves, in D0 and C0. Each of them is, of course, 28 bits, right? 28 bits here, 28 bits here, is together 56 bits. And what happens then is you see the thing LS1. Okay, so that's the next element we want to discuss. That would be number B. LSI, I call that, because, and then I runs through, LSI runs 1, 2, 3 up to 16. That's it's called left shift. What it really is, it's a little bit inexact. It's really a left rotate. It's also eine Rotation. It's not just shifting to the left, but shifting to the left. And then the bits that fall down, that drop down here, they're put in at the right-hand side again. Okay? And it's very specific by how many positions you shift. Right? I mean, you have bits of 28 bits length, and you shift them to the left. Now the big question is, do we shift by 1 position, 2 positions, 3 positions, 4 positions, up to 27 positions, right? Or rotate, right? And this is very specific, namely LSI does the following number of shifts. This is either 1 position shift for the rounds I equal 1, 2, 9, and 16. So for those 4 rounds, the left shift does a bit shift by 1 bit position. Okay, everything shifts left by 1 position. In all the other rounds, 2 position shift for all other I. Okay, that means 3, 4, and so forth, but not 9 and 16. Okay. One funny thing that's happening due to this shift, note, beachte, total number of bit position shifted is the following. So there are 4 rounds where we shift by 1 bit, right? The round number 1, 2, 9, and 16, we rotate by 1 position. So this is 4 times 1. And how many rounds are left? So there are 4 rounds where we shift by 1 position. How many rounds are there where we shift by 2 positions here? 12, right? The 16 rounds, 4 rounds, we shift only 1 position. There's 12 other positions, right? Plus 12.2, so this is 4 plus 24 ist 28. So 28 positions, okay. And that should sound familiar because this number 28 comes up a few times in this block diagram over there, right? So we have, because we have 28 bits here. So what's happening, we start with C0, 28 bits. We do a 1 bit shift here, a 1 bit shift here, and then in most other rounds we shift by two positions. And we only, this rotation only happens within C0. So there's no crosstalk, kein Übersprechen between C0 and D0, right? This is a hard boundary here. Okay, so you only shift within this 28 bits. And what we just figured out, by the time we end up at LS16, at the last left shift, at this point, you see the cursor here. Oops, that's not what I wanted to do. By the point at the time I'm at this cursor here, at this arrow on the file, I've rotated 28 position. What does this mean? What is C16 equal to here? It says, yeah, you got the idea, right? C16 is exactly the same value as C0. It's just, you rotate 1 bit, 2 bits, 2 bits, 2 bits, 2 bits. You keep rotating, and once you rotate it 28 times, you're there. Okay, so that's a little Beobachtung, little observation. C16 equals C0, and D16 equals D0. We'll need that later when we talk about decryption. Right now, this is just some kind of funny observation. We don't need that at the moment, but later this will be very useful. Okay, so what else do we need to know about the key schedule? So we talked about PC1, C0, D0 are just registers. We talked about the rotation elements here. And what's happening then here we have 28 bits, so 56 bits together. They are fed in this other box, PC2, so that is the third and last element. PC2 stands for permuted choice number 2. And what this does essentially is in a different representation is you go on with 56 bits. So this is PC2. And the output equals 48 bits. And so what's happening here is, again, 8 bits are dropped, fallen gelassen, nicht durchverbunden, right? You go in with 56 bits and 8 bits are not connected through. So what's left is 48 bits, but they're also permuted, permutiert, verwürfelt, right? So, and this output, what you get out of here, this is your sub-key KI already, okay? This is exactly what's on the slide, what's in the textbook, blah, 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 okay? So what's happening here is 8 bits are dropped. Again, fallen gelassen, right? So they're not connected through. The remaining (48) input bits are permuted. So what is important here, I don't know whether it's important. What is interesting is if you compare DES with modern ciphers, is a very, very, very simple way of generating subkeys. Modern ciphers have a much more complicated key schedule, Schlüsselfahrplan. I don't know whether that's clear. I always have problem when I'm teaching that. I've been teaching crypto a lot in my life. But I don't know whether that's clear to you. So what's happening is we have 48 bits here, okay? And now if I ask you, what is the relationship of those 48 bits to these original 56 bits, okay? What is important here, we don't do any mathematical operations. So there is no XOR, there's no AND gate, we don't do any Laplace transform, we are not doing any matrix operation, we don't solve quadratic equations. You know what I'm saying here? The only thing is, what we're doing is here, we play with wires, okay? There's not a single Boolean gate, keine einzige Boolsche Funktion is involved here. No gate is active. That means those 48 bits are just a selection of those 56 bits. Okay, if you see here, we just rotate. You know, rotate is a form of permutation. And here we do another permutation. That means these 48 bits are just a selection of certain 50, you know, the 56 bits coming in. You pick certain 48 bits, and this is your subkey K1. K2 is the same story. Again, here there's no Boolean operation, there's no S boxes, there's no math involved. The only thing what you do is permute in a specific way. That means K2, which you don't see here, it should be here where the cursor is, right? That's another 48 bit. Again, these 48 bits are direct connections from the original key. But the interesting thing, the smart thing in the key schedule is that these are very specific key positions that you use in every round, okay? But again, keep in mind, this is only, I may want to write that down, observation, Beobachtung. Each key, K1 up to K16, ist merely, das heißt bloß, kaum, merely, very fancy English, is merely a permutation of the original 56-bit key. Any questions? There isn't any really big, huge theory behind it that I can teach here. Ja, eine Frage. Yeah. Good point. So what he's saying, this is an excellent remark. This shift is just a shift is a type of permutation, right? It's a very extremely regular type of permutation, followed by another permutation. So what he said is that we could merge the left shift and this permutation in one other permutation, in one single permutation. Okay, we could do that, right? But why do they do it this way? Does anyone have? Yeah. Nee. Weil es einen anderen. Let's do that in German, yeah. Yeah. Very good. Yeah, very good. I switched to German for 45 seconds. Wenn wir das machen werden, könnten wir so machen. Das Problem wäre, also war gute Frage und war gute Antwort. Wenn wir das machen würden, bräuchten wir für jeden Unterschlüssel, also für K1, K2 bis K16, 16 verschiedene Schlüsselpermutationen. Da hätten wir so ein PC 2, 3, 4 bis PC 17. Und so hat man einen Left Shift, da müssen Sie nur unterscheiden, 1 oder 2 Positionen, ein PC 2. Aber zum Beispiel in Software, wo heute Speicher kein Problem mehr ist, können Sie das zum Beispiel so machen. Da brauchen Sie das nicht unbedingt so zu machen. Okay? Excellent remark. Very good question. Very smart students. Okay, so we're done with chapter number 1, key schedule. Now comes the most important part of today, the decryption. Okay? Please wake up. Please stop talking. Okay, next 15 minutes are the highlight. After that, you can slowly go back to sleep. Okay, please be awake. Please don't talk. Please don't talk up there. Don't talk. So we start with. Chapter number 2 of today is the encryption. Okay. So first, let's get an idea. What do we want to do? So let's recall how this works. And I do a rather complicated drawing. I don't know whether it's worth that you copy that. You know what I'm saying? Ich schreibe hier was ziemlich Längliches, vielleicht lohnt es sich nicht, das aufzuschreiben, zu kopieren. Das ist nicht sehr kompliziert, okay? But you can do whatever you want. So, encryption side, Alice, okay? Alice is encrypt. So what's happening? First we had this initial permutation, and then we had 16 rounds. So this was round 1. Okay, and at the end we had round 15. Round 16. We had the final permutation, IP minus 1. What we get out is Y, okay? So this is essentially what we did last week, okay? Now what happens on the receiver side? You know, this is being sent over the channel. This is here. Email, right? You encrypt email. This is the internet, okay? It receives, it arrives at the other side at Bob, right? Alice and Bob in cryptography. So what does Bob do? Bob does a decryption, and the basic idea of decryption of any block ciphers is that you reverse that. The first thing that you have to reverse, you have to start here. So what was the last thing that we did? We did the IP minus 1. So we do the regular IP, which is the inverse of this. Okay, that's the first thing that you get. And then what happens in every block cipher, you have again round 1 here, but that might or might not be different. It might be different from this round. So we use an index here, namely index D, and here we use index E for encryption. Okay, so here we have round R1D followed by the second decryption round, and so forth. And at the end, you have the last round of decryption. And what happens in this, you do have another final permutation, IP minus 1, and you get X out. Okay, so that's the basic idea of this decryption. Okay, so and now it's the first time you have to wake up. Okay. So the basic idea, and it's not very complicated, but you must be aware that this is happening, even if it's seemingly trivial. It's not complicated. You start with the decryption. Again, this permutation does the inverse of this permutation. Everybody here, wake up. Don't check, don't do YouTube. Don't read, don't learn. So, now is very important sentence, very Very simple. Don't talk. Hey, don't talk here. This round is the inverse of this round. It's not very deep, right? This round undoes this round, and so forth, okay? That means R16 is the inverse of which round? Is the opposite of which round? For R1. That's the basic idea. So you can, as you go down, graphically, as you go down the decryption, you go up in the encryption here, right? You have something like this. And then the hope is if everything works out, at the end of R16 decryption, we're at this point here, right? This point is equal to this point. And then here we had an IP operation, a permutation, and here we do the inverse, and then we get XOR. So that's the basic idea. So the only question left is how do we inverse one of these rounds? The good thing about this, and pretty much all block ciphers, the rounds are more or less identical. They just have different input parameters. So what we have to do now, the hard part really of this lecture today, the difficult part is to show how do we reverse one round. Okay, once we know how to reverse R16, we can reverse R15 and R14, R13, and so forth. So that's why I said, please wake up, because this is now the thing that's a little bit complicated. Okay, now comes the drawing of today. Okay. Our goal for today, maybe I think I've write that down on here. Ziel. Goal is show that R1D reverses, also invertiert, reverses R16 encryption, okay. Once we can show that, we're done, okay. And I think what I show you by now so this is, I hope this works. Yeah. So what this is, this looks like DES, right? But it's not DES. This is DES decryption. That's the inverse DES in decryption mode. Okay. The first thing that we notice is this looks the same, right? Doesn't this look the same? Pretty much. This is DES inverse, and this is regular DES. Regular, inverse, regular, inverse, regular, inverse. Okay. They look really, I know, it's very exciting. So so the only things that are different, I have this little Ds, I don't know, can you even read them? There's index D, Hochzahl D for decryption, but this is just a name. The functions, they look completely the same. I switch back to the encryption here. They look exactly the same. But what is different here? There's one parameter, one variable. The keys are reversed, right? I start with K16 and go down to K1, which has somehow to do with this thing, with the fact here. Here I had R16, and here's R1. So if I want to reverse R16 and I used K16 at this point, maybe it's a good idea to use K16 at this point too, okay? And now we're going to show all the details. Why is it that we can use the same function, okay? So for doing that, we look at round R16 at the end of this is the end of encryption. L15, R15. We have the f function here. The output of the f function is XORed with L15. This becomes L16, R16. Okay. Then comes the initial final permutation. You have to be careful. This is IP minus 1. You swap the two halves. They werden vertauscht. So the left-hand side is going to the right side, and the right side is going to the left side. And what you get out are 64 bits, and this is what we call Y. That's our ciphertext. Okay? And now we look at the beginning of decryption. So exactly what you see there. So what's happening again, Y is being put on the top here, right? This is now Y. IP, this is just what you see on the top there. I'm just copying what you see on the projector. Now I have to draw another Feistel round. We have L1, R1. 0, sorry, L0, R0. This is what I'm using there too, yeah. Okay. We have again the f function. And then it's the end of the first round. I use the names L1 and R1. Okay. Okay, so what do I want to show? I want to show that L1 and R1 must be equal to which variables? What is the goal? What I want to prove that decryption works. I want to show that this reverses this. Okay. So by the time I'm here, which values should I have? Should have L1 and R1 in terms of these variables here. Do you know what I'm asking you? Yep. Exactly. What I have to show you once I'm here, I have the same values that I had here at this point. Okay, it's very simple. And it turns out, and now what I need to keep the L's and R separated from the encryption decryption, again I use indices. So this is E for encryption. If you want to be exact, you use parentheses, Klammern with this, and I'm not doing that here. It's because it's too much. It's getting too messy. So here I use the D as an index. So what I want to show is L1D is equal, and it's not equal to L15 but to R15. They're swapped, but this is part of Feistel. This is equal, and this is a logical and R1 decryption is equal to L15 encryption. Okay, and it's much easier than you think. Okay, so but again, please listen. Okay, otherwise it's a complete waste that you hear. I mean, the next 3 minutes is this thing that's not trivial, and that's pretty hard. It will take you 90 minutes if you do that Sunday at home, okay? So please pay attention for 3 minutes and you saved 90 minutes of work at home. We start by looking at, where do we start? We start at L1D. Okay, and let's maybe use color. So where's L1D coming from? We go back in time, so to speak. We go here, okay. So this is equal to R0D, okay. Where's R0 coming from? Well, this is kind of the right-hand side of this, so this is equal to L16E here, and it's equal to R15E, okay? So this is immediately clear that this is proof by color, Beweis durch Farbe, right? So mathematicians, I hate that, what I just did, okay? So, but it's correct. So we do a little bit of math in the next one. That was easy. So what's really happening here, this is just connected through, right? You start with R15. This R15 is not encrypted in the last round. You pass that on into this position. You swap that. This is permuted and permuted again. You end up here, and here it's copied over to this point, okay? So nothing happens. That means those 32 bits, this is 32 bits, bit by bit is exactly the same value you see here, okay? There's nothing mysterious. This is how Feistel networks work, okay? The interesting thing is the other part, and it's not really that surprising because we know R15 is not encrypted in this round. What is being encrypted is L15, so this is really the interesting thing. And we start, at this point, we start from the bottom. We want to have an expression for this here, okay? What is this? This is R1D is equal to L0 here, this value, XORed with the F function, and the F function has the following parameter. Let's call that Ki for now, Ki. So let's decide on that later what we want to use. Ki and R0D. Okay. It turns out that L0D, if we go back in time, was going through IP. This is this variable here, and it's this variable here. Okay, so L0D is the value at this point here, okay? It's the output of this XOR gate. So what we do now, we replace L0D by, what is this here? This is L15 plus this F function here, okay? Plus, I mean XOR. L15 plus this F function is this value here. So this becomes L15E plus F function of what? F of R15E. No, sorry. It's the other way around. First the subkey, and here obviously we use K16, right? So this is K16, comma, R15 encryption, okay? There's a lot of indexes, then it's very confusing, and that's why I ask you to wake up, because it's confusing if you do that at home. So what I did here is just this replacement. So this is L0D. This is a red line. If you like colors. Okay. Plus this expression, plus the other f function, f of ki, comma R0D. And now, please pay attention. This is the one minute in this whole 90 minutes that's really interesting, okay? What you want to show, we want to show that R1D, that means that this is equal to this expression. So we want to show this is equal to this, okay? And we're almost there, right? This is equal to that, but unfortunately, we have all this other stuff going on here, right? So what do we want to show? What do we need to show? All of this must vanish, muss verschwinden. Vanish, verschwinden means being equal to 0, right? So how do we force f plus f to be 0? What is the condition for that? If you have an XOR here, there must be the same, right? If you XOR the same value to itself, right? 0 XOR 0 is 0. 1 XOR 1 is 0, right? So we need those. When I say f here, I mean this point here, right? This value. These 32 bits must be identical to these 32 bits. How do we get that? Well, probably the two inputs must be the same of the f function, right? It's a deterministic function, blah, 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 blah. It looks pretty good because we have, did I something do wrong? R0, because R0D is in fact equal, yeah. Now I do one more substitution, eine Ersetzung. Nämlich R0D here at this point, we showed before that the green line, it goes up here, is equal to R15E. Okay? So now these two expressions, they look almost the same. The only thing I have to fix I here, I have to choose the right subkey. Which subkey do I need? Which value for I do I need here? 16, obviously, right? You can't choose K7, right? That's a different bit value. You need K16. That means at this point, I have to fix the subkey. Okay. And now is the big moment. These two expressions cancel, so this is L15E XOR, I don't know, 0, right? This is 32 zeros, right? Just to make it abundantly clear what's going on here. So this is L15E. QED, one of the few times we did a more or less clean proof in this lecture. Okay. The remaining round reversals work the same. Round 2 D reverses round 15 encryption, and so forth. And at the end, the decryption round 16 reverses round 1 encryption. Okay. That's it. Now you can go back to sleep. That was the hard part of the lecture, and it wasn't really that complicated. Okay, so that finishes chapter number 2 of today. And now I really going to present some Faktenwissen, factual knowledge, which is not terribly relevant for the homework. And sometimes we have some simple question in the exam, but I think it's more like the Allgemeinbildung, knowing about modern cryptography. So third section is the security of DES, security of the data encryption standard. And roughly speaking, there are two families of attack. So the two principal ways of attacking DES, and actually the two principal ways mathematically, algorithmically attacking crypto algorithms. The two things you can do. And I'll start with the hard part. I start the A is, I call them analytical attacks, analytische Attacken, analytical attacks. And brute force, exactly. Brute force is the other one, and we start with the fancy one, right, with the schicken, okay? So the big question was, how can we attack them analytically? And I told this anecdote last week. People tried really, really hard, starting in 1975, when DES was announced, to break that mathematically, analytically. They didn't succeed until 1999, when Eli Biham and Adi Shamir found an attack which was called differential. Very good. Exactly, there's differential cryptanalysis. Okay, and people were really excited and said, let's break DES, and it turned out DES is very well protected against this attack, and the best thing you can do nowadays is this requires in very optimistic assumptions, that means chosen plaintext attacks. That means you can choose your inputs 2 to the 7 XY pairs. Okay, means you can break DES, but as with 2 to the 47 steps, so that seems much better than 2 to 56, like brute force. The problem is you have to know 2 to the 47 X values and Y values. The problem is normally as an attacker, you only know the Y values, right? You only know the ciphertext. You don't know 2 to the 47. If you do the math, this is a few terabyte of plaintext you have to know. And again, under one key, if you have a good protocol and you change the key once in a while, this is useless. So even though this is, mathematically, this is better than brute force, it never works in practice. This is it's really hard to construct a situation where you get that amount of plaintext and ciphertext. That was 1990. And then in 1993, a different mathematical attack came up, which has a similar name, which is called linear cryptanalysis by Matsui, a Japanese researcher, a very famous person. And this is a little bit better, but unfortunately only a little bit better. So he reduced the number of required plaintext ciphertext to 2 to the 43. Is still, still terabytes of plaintext ciphertext. And to make things worse, you have to choose them. You can't use random X and Y's. As an attacker, you have to dictate, which values X has, for instance. It doesn't work, okay? So even though mathematically they're impressive, they're complexity-wise, they're better than brute force, they're not super relevant in practice, okay? So that's analytical attacks. Unfortunately, there are other attacks out there. B, the simpler attacks, are brute force attack. So the idea here is just to sketch that. We always talk about brute force attack, but never really show how that works. Let's say you have x0 and y0 as an attacker, and only one block. That means 8 bytes, right, in this. 8 ASCII character. Can be like the header of a file that's being encrypted or some other non-plain text. So what you do as an attacker, very often you decrypt. You decrypt y0, you check, and that's a notation I invented, okay? This is nobody else does that. But I think it's pretty telling. So is this equal to x0? And you check that for all possible keys. That means you're running through ki here, and I ranges from 0, 1, up to 2 to the 56 minus 1, okay? That's the idea. Okay. So the big question is, and was for many, many years, how complicated is it to run such a brute force attack? And it turns out, and people thought, oh, it's easy to do, but actually nobody did it. And there were some, in the 1980s, there were some cost estimates and said, it's $20 million to build such a machine, which would be too expensive for you and even too expensive for me as a German professor. But then the assumption was at an intelligence agency, in Nachrichtendienste, they could do it, and national security agency and stuff. It turns out it's pretty hard to do. And the first time there was a real proof, and there was a big event, was in 1998, is that right? Yeah, in summer 1998. It was called Decryption, which is a special purpose DES hardware cracker. Okay. And you could break DES in a few days, and it was about $250,000. Okay. It was actually built. That's the big thing. Really, I know the people, Ben Yun and Paul Kocher, people we know quite well. They built it, and it was super cool. They did it, they showed it. It's really unsecure what you use. That was the statement, that was their motivation. Said, don't use DES anymore. We can do that with essentially Bordmittel. It's a lot of money, but essentially every big company who wants to break DES could afford $250,000 and break DES. This is what it showed, right? So this was kind of let's say the official death of DES, right? There was New York Times headline, really big news here. The US data encryption standard is not secure anymore, okay? And that coincided with the announcement of AES, so the successor already had started, but it did put more pressure on the US politicians and created US policies to get rid of DES. This is bad. This is not modern cryptography. It can be broken. What we did, much later, 9 years later, we built Copacabana, and this is right, that Tim Gunese showed that to you the first week. Yeah. So we did the same, essentially, that they did, but we had much nicer toys available. Was exactly the same, special purpose hardware cracker, blah, 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 blah. The small difference is we paid it was about $10,000, okay? And it's not that we are much smarter than they are, we're not. I think they're probably the better computer engineers, but the technology had evolved. we could buy off-the-shelf chips, FPGA, reprogrammable hardware chips. There are practica labs later on where you can learn about that hardware chips that you can program. We bought them. They were the actual chips were only a few thousand euros here, and then we could do it. And now we have actually the next generation, Riviera, the next version of Copacabana can do. I think our record is right now 1.5 days. Okay, so it's not very hard. So, yeah. Wir haben ein paar produziert und die gehen an Ermittlungsbehörden. Okay. So no, but okay, let's switch. So what surprised us? We thought when we built that we would get a lot of requests from questionable people. We didn't. There were, I think, once or twice, and this is now 3 years ago, that people contacted us, and essentially it was pretty clear they wanted to break cars or hack into payment terminals. But that's it. There were, 2 times we got weird emails, and we said, what is your application? Tell us about you, and you never get an email back, right? So that's the end of the story. So, and the main application is there's some older standards where they need that for where DES is being used for computing passwords, for hashing passwords. And that's where the application in law enforcement, mit Polizeibehörden, who likes that. Okay. But, yeah. Okay. So, DES can be broken in a few days. Okay, which really means don't use DES anymore, okay? You wasted the last 2 weeks. This is what it says there, okay? DES is unsecure. Why do you come to the lecture? DES is a stupid algorithm, right? But, and this is number 4, and this is only a few more minutes, the question is, what do we do instead? So what are the Okay, so this is kryptographische Allgemeinbildung. This is very important what I show you here. The number 1 replacement, der normale Ersatz, the default, the standard thing, if you choose a block cipher, should be AES. This is the advanced encryption standard. We're going to talk about it the next 2 weeks. Super important, okay? This is the de facto world standard. Very secure, very fast, particularly in software, so there aren't any good reasons not to use AES. There's no patents on it, blah, 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 blah. Huge success story, okay? In my opinion, as a humble, bescheidener applied cryptographer, I think the main the biggest drawback, if there's any drawback, if you want to have really cheap hardware, it's not very small in hardware. So there's some applications, such as the German E-Pass, right, the new electronic passport. They don't have AES on board. What they have on board is triple DES. So what you do, you're not encrypting plaintext once with DES, but you encrypt it 1, 2, 3 times in a row, okay, with 3 different keys usually, and we're going to talk more about that in a few weeks. This is still, let's put it this way, still very secure. Okay, triple DES is very secure. Okay. What else can we do? Are these all the algorithms that are out there? No. I mean, if you look for block cipher proposals, there's something like 200 block ciphers, I believe, have been proposed. I once had a Ph.D. student, a doctoral student, doctorand, and he wanted to classify all the algorithm, and that was 10 years ago, and he stopped at cipher 100. So he counted them, he wrote input-output parameters and kind of and all the internal function classification. He stopped at cipher 100, so there are a huge number of ciphers out there. But there are a few one I want to name, probably the most prominent one, finalists. IS finalist, what is that? I'm going to talk next week about AES. Actually, in 2 weeks, I'm going to talk about the history of AES. And there was a public competition, so there were many algorithms were submitted, eingereicht to the US standard body. And in the last round, there were 5 algorithms left. One became the AES standards, but there were 4 other ones that didn't win. And they're all very, very secure. It's not that they were unsecure and not chosen, there were other reasons. So they are all 4 ciphers, all very secure. So they know, to my knowledge, I should probably check again, but to my knowledge, there's no attacks known to any of the 4 other algorithms there. And they're named in the books. This is RC6, Mars, Serpent, and another one. Okay, so there are 4 algorithms, and then that's it for now. Okay, so these, just that we've heard the names, we stop at this point. Thank you very much. We start with AES next week.